This talk is the third talk regarding artifacts. It is intended for the Clinical Neurophysiology Fellows at Nicklaus Children's Hospital. It will be conducted in a question and answer format. I will start right where the second talk left off. So the first question is, which of the following is not true regarding Electropop? A. Sudden change in capacitance at the scalp electrode interface. B. Resemble calibration signals. C. Cannot resemble an abnormal epileptiform discharge. D. Is usually low voltage. This is an electropop. It is due to the release of a charge stored in the capacitor, which is formed by the electrode and the skin. This discharge produces a sudden direct current potential that is represented in the given channel. Here I am pointing to another electropop, and here to a third one. In the classic form, electropops form a triangular wave with a fast up and a slow down deviation. This quality is shared with interictal epileptiform activity, but in epileptiform discharges, the rise is not as steep as it is in an electropop. This is another of the electropop I showed you in the prior epoch. As you can see, it is a more square element. Overall, electropops tend to be positive. They occur because of loose connections, corrosion of the electrodes, drying of the electrode paste, or a poor connection between the electrode and the amplifier. In this case, you can see that the last pop occurred during a movement. So the answer to this question is C. Next question. Which of the following is not a feature of interictal epileptiform discharges? A. Crossing the baseline after the first component. B. Rise time faster than fall time. C. Pre-spike background disruption. D. None of the above. This is a cartoonish idealization of an interictal epileptiform wave. Interictal epileptiform activity has a duration between 20 to 70 milliseconds, in which case is called a spike, or 70 to 200 milliseconds, in which case is called a sharp wave. Current thinking does not give different meaning to these two types of electrical activity. Interictal epileptiform activity have a faster rise time, represented in yellow, and a slower drop time, represented in blue in this frame. They cross the previously established baseline, therefore they are biphasic or triphasics. They are followed by a wave slower than those presented before the spike or sharp wave, which may be in the same direction as shown here or have an opposite polarity. They are preceded by a change in the background rhythm and followed by a background disruption. The background disruption goes beyond the single slow wave that appeared after the spike. They can be mapped to a logical field. They are usually negative except in infants and neonates. They arise most frequently from the anterior and mid-temporal regions or at the vertex. In these regions, the probability of a seizure when a spike occurs in one of these regions is over 85%. If, on the other hand, the activity is present in the central, frontal, or occipital region, the likelihood of it being linked to seizure is less than 75%. For Peter Gore, a famous neurophysiologist, he believed that parameters 1 and 3 are most reliable in distinguishing epileptiform activity from non-epileptiform activity, and that at the time of making a decision, they should weigh more in the process than any other parameter. In this frame, I am representing a cartoonish representation of a non-interepileptiform wave in aqua and superimposing it to an idealized interictal activity in yellow. So the answer to this question is D. Next question. All electrode artifacts are positive when referring to electrode pops. A true, B false. This frame shows a small artifact preceding a few electrode pops that, as you can see, are negative at D3. This is followed by a slow wave, also likely due to electrode artifact due to poor connections between the electrode and the scalp. This is a very low voltage square-like activity arising from the PC electrode, which is also an artifact. This is an electrode artifact arising from O1 triggered by padding. It looks just like an EKG artifact, but it does not coincide with the EKG channel. In this frame, there is an electrode artifact manifested by a slow wave with a sharp component due to EKG intervenence in the artifact. This is another example of electrode artifact. T4 is bad, and as you can see, F8 is worse. So the answer to this question is false. Next question. Please look at this frame and try to choose the best answer. So here we need to distinguish if we're dealing with an artifact or seizure activity. The first step when determining if an activity is artifactual or a seizure is to map the field. Seizures, except in neonates, create a field that involves more than one electrode. In this case, the activity is restricted to one electrode. So we put 1 in the no seizure column, but still we may have doubt if this activity is or is not a seizure. So we go to the next step that consists of determining the evolution of the shape of the individual wave within the rhythmic activity. The individual wave of an ictal epileptiform rhythm for the most part maintains their shape, and when they change, the change tends to be rather small and gradual. As you can see in this frame, the changes that are occurring tend to be small and gradual. Therefore, we put 1 check mark in the seizure column. The third step is to determine the evolution of the duration of the individual waves within the rhythmic activity. The individual wave of an ictal epileptiform rhythm usually increases gradually as time goes by, and then decreases. Again, in this epoch, the activity seems to increase in duration as time goes by and does so gradually. So we put a check mark in the seizure column. We then take a fourth step. This step consists of determining the evolution of the amplitude of the individual wave within the rhythmic activity. In ictal epileptiform rhythm, the individual waves usually change gradually in duration and amplitude as time goes by. In this case, we are concerned with amplitude. The amplitude does not change significantly in this case, as you can see. So we place a check mark in the no seizure column. And move on to the fifth step. This step consists of determining the spatial evolution of the rhythmic activity as a whole, usually seizures, that is, ictal epileptiform activity that starts in one derivation spread to contiguous derivation, reflecting an orderly geographical expansion of the ictal activity. Whereas in the case of artifacts, the spread tends not to be orderly. They go from one derivation to another one, sparing derivations in the middle. In this epoch, there is no spread at all. So we put a check mark in the no seizure column. And move on to the sixth step. This step consists of determining the temporal evolution of the rhythmic activity. It is done by considering the inter-discharge interval, not the peak-to-peak distance. In epileptiform activity, there is a progressive increase in the inter-discharge interval, which is usually absent in artifactual rhythms. This epoch, as you can see, reflects that the inter-discharge distance progressively increases. So we place a check mark in the seizure column. And we go to the seventh step. This step consists of clinical or video observation of the actual event. But in this case, we do not have it. So we move on to the eighth step, which is to correlate the possible sources of artifact most resembling the artifact in question. This was done in this patient, and the artifact was gone. So we put a check mark in the no seizure column. So we ended up determining that this event was not a seizure. The fact that the activity in question disappeared once the electrode was changed overwhelms all other considerations. Therefore, the answer to this question is true. Next question. Single electrode artifacts can be produced by A. Faulty electrode or electrode scalp interface, B. Faulty input box or head box or cable, C. Faulty input switch selector inside the machine, D. All of the above. Single electrode artifacts can be produced by electrodes, input box, input cable, or input selector switches problems. In the digital machine, the input selector switches are software, and they can be accessed in every EEG recording. So the answer to this question is all of the above. When should you think of an electrode, input box, input cable, or input switch selector fault? A. When radically different activity is present. B. Activity not blending. C. Activity traced to one electrode. D. All of the above. You should think of a flaw in any of these elements when the activity present in the tracing becomes radically different from the previous activity. When the activity does not blend with other simultaneously occurring activity, and when the activity appears only in one channel. So the answer to this question is all of the above. Next question. Incremental artifacts arise from the EEG machine. A. True, B. False. I will use the term instrumental artifacts to refer to all artifacts arising from the solid EEG machine. In general, I will divide these artifacts in three groups. Group 1, those produced by the amplifier, anti-aliasing filters, and all other electrical elements of the solid EEG machine. Number 2, those arising from the software and computer modules. And number 3, those arising from the screen. So the answer to this question is true. Next question. EEG machine, electrical cord, wall electrical cables, people, and all electrical equipment surrounding a patient can produce A. Capacitant artifact, B. Inductive artifact, C. Electrostatic artifacts, D. All of the above. The properties of electricity and all electrical components used in hospitals and offices produces induction, capacitant, static electricity, and magnetic artifacts. This is an example of capacitant artifact resembling brain activity produced by checking the input cable even when the input cable was disconnected from a patient. You can imagine how many potential artifacts can occur in an OR. One of them is not to be forgotten, which is the one produced by line isolation monitors. This is a machine that is often used to measure leakage from the electrical sockets. And at times it is forgotten in the OR and it produces a significant amount of 60 Hz artifacts. In addition, macro IV drips can produce artifacts by induction. Here I have compressed the activity. Just you can look at the time segment here, that is 1 second, is very small, in order for us to see the rhythmicity of the fluid drop. This is a frame demonstrating a ring artifact, As you can imagine, this is a combination of inductive and magnetic artifact. So the answer to this question is D, all of the above. Next question. EEG-artifacts are produced by a person walking close to a recording EEG machine. A, capacitance. B, inductive. C, electrostatic. D, all of the above. Movement of people can produce artifacts. This is an example of an artifact produced by movement of individuals around or close to the EEG machine. This type of artifact is produced by static electricity, so we consider it an electrostatic artifact. This type of artifact usually produces a slow activity with multiple phases and an illogical polarity. So the answer to this question is C. Next question. Please look at this frame and decide. A, watering tube. B, closokinetic artifact. C, ECMO artifact. D, bridge artifact. This artifact is seen in cases where there's water in the tube of the ventilator. So the answer to this question is A. Next question. Please look at this frame and choose the best answer. This is an ECMO machine, and the artifact that you just saw is the type that we tend to see in patients undergoing ECMO. So the answer to this question is A. Next question. Which of the following steps reduces 60 Hz artifacts? A, keep all electrodes, wire, and cable short. B, bundling electrodes wired as a group. C, unplugging unnecessary equipment. D, all of the above. Steps to reduce 60 Hz artifacts include keeping all electrodes wired and cables short, bundling electrodes wired as a group. These conditions are reflected in this frame. Electrodes should be short and they should be bundled together and stranded, as you can see in this diagram. Another important step in reducing 60 Hz artifacts is to unplug all unnecessary equipment. For example, we may be able to eliminate many of the equipment that we think that we need when we are conducting an EEG without affecting the patient. But then again, that is for the clinician to decide. The fourth step that we can take to reduce 60 Hz artifact is to use the notch filter. It is important to realize that using the notch filter will also distort other important EEG activities, and that not all 60 Hz notch filters are the same. Some notch filters have a very steep roll-off and as such will not significantly affect any activity other than 60 Hz activity, whereas others, usually those in the older machines, have a less steep filter, thus reducing the amplitude of wave even as distant from 60 Hz as 10 Hz and 100 Hz. So the answer to this question is D. Next question. Which of the following is not true regarding amplifier noise? A is produced by thermal agitation of electrons. B. Only contains 60 Hz electrical frequencies in the United States and 50 Hz in England. C. The wider the bandwidth of the amplifier, the more noise artifact will appear. D. The lower the sensitivity, the more troublesome noise artifact will become. Amplifiers are an important component of the EEG machine that we may find at multiple locations within the EEG machine. Here I just signaled 2 of those locations. In the next few seconds, I will mention some important points regarding amplifier noise. Amplifier noise is produced by thermal agitation of electrons within the amplifiers. Amplifier noise contains components of all frequencies. The wider the bandwidth of the amplifier, the more noise artifact it will produce. Thus, in addition to 60 Hz artifact, noise amplifier will inject into the tracing artifact of much faster rhythms. The lower the sensitivity that is being used to record an EEG, the more troublesome noise artifacts will become. And amplifiers' bad function will make noise even worse. So the answer to this question is B. Next question. Analog to digital converters do not produce artifacts. A true, B false. Analog digital converters are electrical elements, and as such, they produce artifacts. So the answer to this question is false. Next question. Electrostatic forces generated by dash induced current in electrode wires and cables. A. Movement of electrodes and input cable. B. Piezoelectricity, that is electricity generated by the formation of polymeric material, such as an IV tube. C. Movement of objects, part of an object, or object within an object, such as water in a tube. D. All of the above. Electrostatic artifacts are produced by movement of electrodes and input cables, movement of people, movement of objects, part of an object, or object within an object, such as water in a tube, which we have presented before, and piezoelectric deformation, that is electricity that is generated by deformation of the polymeric material, such as IV tubing. Piezoelectric artifacts travel from the patient to the EEG machine just as cardiac and diaphragmatic pacemaker and vagal stimulator artifacts. So the answer to this question is true. Next question. Electric forces generated by implanted electrical devices within the patient's body produce artifacts. A. True, B. False. Devices that produce electrical artifacts include pacemakers, vagus nerve stimulators, spinal cord stimulators, abdominal electrical stimulators. So the answer to this question is A. Next question. Phone may produce electromagnetic artifacts. A. True, B. False. Electromagnetic artifacts are produced by forces generated by TV, radio, phones, electrocauterizing devices, infusion pump, line isolation monitors. This is an example of phone artifact, which is either or is a combination of inductive and magnetic artifacts. Line isolation monitor is used to scan the outlets for leakage, can produce very similar artifacts as 60 Hz. So the answer to this question is true. Next question. Slew error are considered digital artifacts. A, true, B, false. I like to save the term digital artifacts to the artifacts that occur after the analog signal is converted to digital, but most books tend not to do so. The following are considered digital artifacts in many books. I have listed them in this frame and will mention each of them individually in the next few frames. Aliasing, which means undersampling, creates spurious low frequencies. You can see in this new frame how when the sampling is done at 16 Hz, there is a significant amount of activity in the 5, 6, and 7 Hz, despite the fact that the ongoing activity is 8 Hz. Below that, you can see that when sampled at 64 Hz, 8 Hz activity only contains 8 Hz rhythm once it is translated to digital. This again is an example of 8 Hz activity. It's sampled at 16 Hz and produce some spurious activity in the 5 and 6 and 7 Hz range. But when we sample at 64 Hz, that is 64 times per second, it does not produce any activity other than 8 Hz. A slew error refers to time axis distortion, which means lag time between acquisition and display. All information is acquired at the same time, but not displayed instantly. The one on top is displayed before the one in the bottom. The way to solve this is by using new equipment that have what is called sample and hold devices, which they take all the data and then put the data into the display all at the same time. Blocking error can occur because of poor functioning amplifiers, which get saturated and then just responds to that saturation with straight lines. Multiplexing errors occur because of an inversion of a set of channels that are managed simultaneously by one amplifier or post-amplifier devices. Notice how the EKG has changed from its original position in the EKG channel to the T8PC channel. Error in analog to digital conversion can also produce failure to convert a specific data point. This type of error is usually referred to as sticky bit error. So the answer to this question is true. Next question. If you have an ADC that samples at 200 Hz and a computer screen representing 10 seconds with a 1000 pixel width, what is the fastest signal you will be able to faithfully represent? A, 50 Hz, B, 60 Hz, C, 40 Hz, D, 70 Hz. Artifacts can also occur due to screen monitor errors. This EEG was captured using a low-resolution screen monitor. The activity has an alpha frequency. That is the activity that is being pointed by the arrow. When viewed with a better monitor, that is more pixels per second, it is obvious that we're dealing with an artifact. In this case, a 60 Hz artifact. It is important to understand that in order to get normal representation of the EEG activity, the highest frequency of waves that can be represented in a computer screen is determined by dividing the number of pixels per second by 2. For example, if a screen can accommodate 100 pixel width per second, it can represent a signal of 50 Hz. And in reality, even that it doesn't do too well. But that's the Nyquist number, so that's the one that you must remember. Smudging artifact, that means aliasing due to poor screen monitor resolution, will occur if we attempt to represent a wave that is more than 1/2 the number of pixels per second. So if we have a monitor that has 100 pixel width per second, if we attempt to represent a signal that is more than 50 Hz, we will produce artifacts by aliasing. This is an example of idealized analog recording of activity of different frequencies. Here is how that activity would look by using a screen with 100 pixel width per second monitor. The 50 Hz activity can be seen but not well. The 100 Hz activity cannot be seen at all. So the answer to this question is A, 50. Theoretically, analog equipment at a sensitivity of 7 microvolts per millimeter can detect 1 microvolt baseline derivations, whereas digital system with 4 pixels per millimeter vertical dimension with the same sensitivity cannot. A, true, B, false. With a thin enough pen, an activity of 1 microvolt could be traced using a sensitivity of 7 microvolts per millimeters. This would not be the case when using a monitor displaying 4 pixels per millimeter. So the answer to this question is true. 60 cycle artifacts in all EEG channels should prompt you to check the ground and if dash period. A, double grounded, make it only one ground. B, poor patient ground connection, fix it. C, one ground with good connection, stop recording. D, all of the above. Troubleshooting regarding artifacts is based on finding the source of the artifact and fixing it. Artifacts can be due to errors everywhere, but some are more dangerous than others. If, while running an EEG, you find 60 Hz artifact in all channels or at least in multiple channels, you may confirm it by slowing down the recordings so as you can see each individual wave better and count them corresponding to 1 second. If it continues, then that indicates the possibility of health hazard. So the best thing to do is to take the electrodes off the patient. So the answer to this question is D. Next question. Artifacts limit to one electrode is always due to a problem with electrodes. A, true, B, false. This is an example of a single electrode artifact. I will use the skeleton of an old EEG machine to indicate the source of single electrode artifacts. They may occur because of a problem at the level of the electrode, the input box, the input cable, or the input selector switch. Input selector switches in current EEG machine, as I pointed out before, is part of the software of the machine. So the answer to this question is false. Next question. A normal impedance excludes the possibility of a bad electrode. A, true, B, false. In the presence of a single electrode artifact, see if the alleged bad electrode is detached. If it is, fix it. If it is not, check if the disc, its connection with the wire, or the wire looks broken. If it is, fix it by changing the electrode. If it is not, see if the paste is dried, and if it is, fix it. If it is not, check impedance. If it is high, the electrode is bad, change it. If it is normal, take the suspected electrode and change it to a good spot in the jackpot box. By doing so, you will have a good electrode inserted in the plug the bad electrode was plugged in before, and a bad electrode where a good electrode was there before. If now you see that the artifact is in the location corresponding to the jackbox, where you just put the bad electrode, then the electrode is bad. If the artifact stays with the location present in the box, then you have to change the box and the cable. If the artifact then stays, the problem is with the machine and you need to change the machine. If the problem is gone, then you had a bad box and you fix the problem. So the answer to this question is false. Next question. Out of phase harmonic of 60 Hz activity produced by electric field generated by adjacent equipment is eliminated by notch filters. A, true, B, false. Some notch filters have a very steep roll-off and as such will not significantly affect any activity not less than 50 Hz or more than 80 Hz. Some other have a less steep roll-off, thus reduce the amplitude of activity in the range of 10 Hz all the way to 100 Hz, but they do so very little. not enough to totally erase an activity, for example, of 20 hertz, which could be a harmonic of 60 hertz. So all notch filters will eliminate 60 hertz activity, but out-of-phase harmonics of 60 activity produced by electric fields generated by adjacent equipment, for example, activity at 20 hertz, will not be eliminated using notch filters. So the answer to this question is false. Next question. Faulty ground as a cause for an artifact can be excluded when the artifact is not present in all channels. A true, B false. In OR, which is a hostile environment, there are many artifacts. Even if the artifact is present in a limited number of electrodes, a poor ground should always be suspected. So the answer to this question is false. Next question. Which of the following steps reduces electromagnetic artifacts? A. Ensuring that all equipment in the room has shielding metal case connected to ground. B. Plugging all equipment into the same connection point. C. Ensuring that all power cables do not run in parallel. D. All of the above. The ways to reduce electromagnetic artifacts are quite a few. The first one is ensuring that all equipment in the room has a shielding metal case connected to ground. The second is plugging all equipment into the same connection point. The third one is ensuring that all power cables do not run in parallel. The fourth one is to place power cables as far as possible from electrode wires and other cables. So the answer to this question is all of the above. Which of the following steps may eliminate electrostatic artifacts? A. Using short electrode cables. B. Bundling wires in plastic tubing. C. Wrapping electrodes in gauze. D. All of the above. The ways to reduce electrostatic artifacts are by using short electrode cables, bundling wires in plastic tubing, and or wrapping electrodes in gauze. Electrodes should be, as it is pointed out in this frame, short, and they should be bundled together and stranded and also covered by plastic material if possible. So the answer to this question is D. Next question. How can you confirm a salt bridge artifact between two electrodes? A. Increase the sensitivity. B. Record each electrode independently to a common reference. C. Decrease paper speed. D. All of the above. The best way to analyze a salt bridge is to record each electrode independently to a common reference, as you can see in this frame. This will bring out the activity in each electrode, which was not present when they both were connected to each other. So the answer to this question is B. Next question. Please take a look at this frame and choose the best answer. I put this question at the end just to make a point, and the point is that when a reason for an artifact is present, for example, a crack in the head, consider any suspicious activity an artifact first, especially if the EEG finding do not match clinical expectations. So the answer to this question is A. Thank you very much for your attention.